So today we are going to deal with another colligative property called as depression in freezing point. Yes. So before going to the depression in the freezing point, first we have to understand that what do you mean by this freezing point? Of course. So it's a temperature at which the vapor pressure of a substance in solid phase, is equal to the vapor pressure in liquid phase. So freezing point means you are determining a temperature at which the vapor pressure of a substance in a solid phase is equal to the vapor pressure in the liquid phase. So now the question arises that what happens to this freezing point when you're adding a solute to that of your solvent? To understand that one, you have to take that when you're considering a beaker filled with your water, of course, and you're closing it. So when you're determining its freezing point, we know that the freezing point of the water is 0 degrees Celsius. But when the same container having the same amount of the water is added from an external source or non-volatile solute, we are very particular of addition of the solute in all the colligative properties. Whatever we are adding is a non-volatile solute. Example is your NaCl. Remember, the freezing point decreases. It is mainly with respect to whatever the vapor pressure we are going to measure. It is only depending upon that one. We are saying that. So with respect to the pure solvent, the freezing point of a solution is less. That is the reason when we say as this colligative property as depression in the freezing point. Coming with respect to the definition of the depression in the freezing point, if I consider as Tf as the temperature or the freezing point, of your solution, that is your solvent plus your non-volatile solute, and Tf naught as the freezing point of your pure solvent, then of course what you can write is delta Tf is equals to, how will you write? Of course we know that the freezing point of the pure solvent is always greater than that of the freezing point of your solution. If you're not able to remember this, you can just note down the heading, depression in the freezing point. I have marked that whenever we are dealing with the colligative properties, whatever the name they have given, that only depends when you are adding a solute. For example, elevation in the boiling point, that is boiling point is increasing when you are adding a solute, hence the term as elevation. Similarly, depression in the freezing point, that means what? Whenever you are adding a solute, there will be a decrease in the freezing point when compared to that of your pure solvent. So how can you write this one? Delta Tf is equals to Tf minus of your Tf naught. So this difference is called as what? Depression in the freezing point. So keeping this one in mind, now we are going to see the derivation part. What is the relationship between that of your depression in the freezing point, that is delta Tf, and molecular mass of your solute. As we have seen, we need some expression in order to derive this. So basically first we are going to see that how this depression in the freezing point is related with respect to the concentration term, that is your molality. Similar to that of your elevation in the boiling point, your depression in the freezing point is also directly proportional to molality. Once again I am saying here M refers to your molality. Yes. So when I'm going to remove this proportionality, sign, I should add a proportionality constant, and here I am adding it a constant which is called as Kf, which is known as cryoscopic constant. What it is called as cryoscopic constant. If you are remembering, when we were dealing with that of your elevation in the boiling point, we have seen a constant Kb which is called as an ebullioscopic constant. But when you are dealing with that of your Tf, that is your depression in the freezing point, we are utilizing a constant which is called as cryoscopic constant. Okay, so if you want to remember it, don't confuse here. See, boiling, B is there. Here also ebullios, B is there. So if you are remembering one constant name, other constant will be easily remembered by you itself. So of course, when we defined the ebullioscopic constant, we saw that it is what? Increase in the boiling point. Why? Because it is an elevation part. So here what should be there? So it is a decrease in the freezing point. Why? Because when the addition of a solute, we are decreasing. The solution's freezing point has been decreased. So next what? When one mole, then remaining all thing will be same itself. Alpha. So it is a decrease in the freezing point when one mole of non-volatile solute is dissolved in 1 kg of solvent. Of course, alva, because we are mainly particular that I am using the concentration as molality, and I know the definition, number of the moles of the solute divided by mass of the solvent in kg. So this decrease is why? Because by the addition of this solute, I have decreased the, or whatever is resulting is a decrease in the freezing point of your solution. So decrease in the freezing point observed when 1 mole of your non-volatile solute is dissolved in 1 kg of your solvent. So this is called as what? As cryoscopic constant. So you have to remember that this Kb, whatever we are calling it, is an ebullioscopic constant. It can be also called as molal, from the term as molality, elevation constant also. Molal elevation constant. Molal means, of course, it is related to molality. Elevation means what? It is an elevation in the boiling point. In that case, we are getting alva, this ebullioscopic constant. That's the reason it is also called as molal elevation constant. Can you say what for Kf we can use? It can be called as molal depression constant. Molal depression constant. It is not that always they have to use the word as cryoscopic or ebullioscopic. They can also use the word as molal elevation constant. You should make sure that you should know that it can also be called as molal elevation constant or a ebullioscopic constant. Similarly, a cryoscopic constant can be also called as molal depression constant. So taking the part that is your delta Tf is equals to Kf into M. So we know that what? M can be written as what? Yes. So it can be written as Wb by Mb, that is your weight of the solute divided by molecular mass of the solute, alpha number of the moles of the solute. Moles can be written in grams by this way, divided by weight of the solvent to the 1000. So when you are substituting in your main expression, you are getting as delta Tf is equals to Kf Wb into 1000 divided by Mb into Wa. But I require what? The molecular mass of the solute, because in all the colligative properties we are determining the molecular mass of the solute. So Mb will be equals to what? You can write Kf Wb into 1000 divided by delta Tf into Wa. So it is similar to that of what we have done for your elevation in the boiling point. There we have to just replace the word as Kb and delta Tb. If you can just go through the expression, you are going to get, because nothing we have changed. Everything is same, but whatever we are saying, the constants are different. But coming with respect to the main theory part, when you are plotting the graph, that is very much important, because our graph itself, so whatever the theory part I am saying, the depression in the freezing point, elevation in the boiling point, is mainly observed when you are seeing those graphs. For example, when I am plotting the graph for depression in the freezing point, that is vapor pressure versus that of your temperature. Remember guys, So when you're taking for a pure solvent and you're going to freeze it, so as the temperature goes on increases, the freezing point of that of your solvent, this is your frozen solvent, goes on increases. This is of your pure solvent and you're going to solidify it. So it is going on increasing. What is increasing? With respect to the temperature, the vapor pressure also goes on increases. That's the thing. But now what happens when to this solvent you are adding certain solute and we are going to freeze it, we could see the nature of the graph in this way. Able to see? Of course. Which is less than that of your solvent. So this is what it is of your solution. So this is my experimental part. I am for different temperatures, I am going to check out my vapor pressure. From that theory, I am able to say that okay, there is a depression in the freezing point observed. So when I am taking, this was when I am doing the solvent in a solid form, but when I am taking the liquid solvent as it is and I am measuring its temperature with respect to vapor pressure, I could see the graph in this way. So which is of this? This is of your liquid solvent. So keeping this one in mind and touching this one over here, extrapolating these lines to the top of your x-axis. So what I'm getting over here, so this is of your solution. What is happening, this is, if I call it as TF, and this is what of your pure solvent, liquid solvent, this will be what TF naught. So here what I'm observing, pure solvent freezing point is very high compared to that of your freezing point of your solution, which is low, because from here itself this is your origin 0, 1, 2, 3, like this it is going. So this TF is smaller than that of your TF naught, which shows that after the addition of the solute, when you are determining the freezing point, of course the freezing point of the solution is less than that of your solvent. Hence we are saying the depression in the freezing point as what? TF naught minus TF. Of course, if you ask me, so then how can you say with respect to elevation in the boiling point? Of course, the same thing, vapor pressure versus your temperature part, yes. So here the graph is in this way. For different temperatures when I am measuring, first whatever the graph I am getting, this is for your solvent, whereas this is for your solution. This is your boiling point of the solvent, boiling point of the solution. So at particular point it has been, I'm taking and I'm just extrapolating it over here. So this is what of your solvent, pure solvent. If I take it as TB naught, the same line when I'm taking and extrapolating it for my solution, you could just see that here I am getting as what? TB, because it is the boiling point of your solution. Here itself we are notifying what? Your TB naught is smaller than that of your TB, which is saying what? After the addition of a solute to this solvent, the solution's boiling point is increased. So it is called as what? Elevation in the boiling point, and that is the reason we are saying as delta TB as TB minus TB naught. So whatever this difference is there, this is called as what? As delta TB. So whatever the difference here we are seeing, so this difference is called as what? Delta TF. So from the experimental part, we are giving you the theoretical part. So of course, the one more most important point I have to just mention you is that the SI unit. So the SI unit of your cryoscopic or that of your, that is your KF and KB, both are same, and you have to remember it's important for 1 mark. It is Kelvin kg per mole. Very much important. So now I hope you have been understood why we are saying as an elevation in the boiling point and the depression in the freezing point. So these are what in this whatever the graph we have plotted, this is giving us whatever the theory we are relating. If you are having any confusion, you can just go through these graphs and you are getting your confusions out. So this was one more colligative property. So in our next video, we are going to see the last colligative property called as that of your osmotic pressure.